Hello and welcome to this star-studded edition of the programme. Maggie and I have emerged cautiously from our homes and we've come here to the University College London Observatory in Mill Hill.
This month, we'll be looking at the life and death of stars. Our local star, the Sun, is firmly in middle age, and recent activity on the surface has been at a minimum, but that's about to change. Lucy Green will be looking at some old drawings to see how they can help us predict how the Sun will behave in the future.
We'll be pondering the strange dimming of Orion's trusty shoulder, Betelgeuse, as well as bringing you news of the most luminous supernova yet observed.
Pete will be attempting some solar observing, and we'll be paying tribute to a stellar pioneer, Margaret Burbidge, who began her career here in Mill Hill. Welcome to the Sky at Night.
The life story of a star begins and ends with drama, whether we're talking about long-lived red dwarfs or giant stars destined to go out with a bang. Their stories shape our universe. Stars are born in vast stellar nurseries called nebulae. Here, gravity works its magic, causing clumps of the gas to collapse. The density rises until suddenly it is large enough that collisions between hydrogen atoms become likely. Nuclear fusion begins, and a star is born.
The destiny of a new star depends largely on its mass. Average stars, like the Sun, burn through their hydrogen fuel slowly and can live for many billions of years.
But the most massive stars are like the rock gods of the universe. They live fast and die young, burning rapidly through their reserves of fuel. The most massive may live for only a few million or even a few 100,000 years, and the end of a star's life varies dramatically, again, depending on its mass. Towards the end of their lives, stars like the Sun first swell to become red giants, before shedding their outer layers as a beautiful planetary nebula, and ending up as a slowly cooling white dwarf.
But the giants have a much more spectacular end. A star with more than 8 times the mass of the Sun will explode as a supernova. Some of the largest explosions in the universe. And will leave behind a dense core that becomes either a neutron star or a black hole. At the end of last year, there was wild speculation online and in the media that one of our most familiar stars was about to go supernova. The speculation was triggered by the sudden and dramatic dimming of Betelgeuse. Located in the top corner of Orion, Betelgeuse is a red supergiant. A massive star that, having burnt through all its hydrogen fuel in its core, is nearing the end of its life.
Supergiants are aptly named. They're staggeringly large. Replace the Sun with Betelgeuse, and its outer surfaces would stretch almost to the orbit of Jupiter. To find out what was really going on with the dimming of Betelgeuse, I spoke to Emily Cannon and Miguel Montague. So I'm delighted you're here to talk about one of my favourite stars. You've been looking at Betelgeuse for many years. Can you tell us about the observations you've made in the past?
So yeah, I started to observe it, I think it was in 2011. So I looked at the surface mainly to look at the convective cells. So it's like what we see on the sun when you have bubbles of gas coming from the deep of the star, where it's warm and it gets cooler at the surface and sink down again. So it's like
a bit like soup boiling, right?
Yeah, exactly. Except that for a red supergiant like Betelgeuse, instead of having millions of these cells like on the sun, you have like 10 of them on a star whose diameter corresponds to the orbit of Jupiter. So they are really few and really, really large.
So its radius is 1,000 times that of the sun. So if you look in terms of that in volume, you're talking about 1 billion suns can fit in just this one star.
When did people notice that Betelgeuse was behaving strangely?
So it's a semi-regular variable star. So it means that it has a change in light. But what was really strange is that normally it should have been in early December, still quite bright, but it was already near the minimum. So that meant that something weird was happening.
Using the Very Large Telescope, or VLT in Chile, Miguel and Emily have been able to take a series of images that resolve actual surface detail of the star. I have to say, they're absolutely stunning to be able to see a star like this. I've got them on my screen. Can you tell me what I'm looking at?
So there are two images, actually, almost a year apart. So the one of January, actually, we went together with Emily to record it in Chile. And you just see a disk. It's what you would expect on a star. When you come back a year after that, so December 2019, basically the southern part is missing. So you see the northern part very clearly, as bright almost, but the southern part is not there.
Okay, so we've got this enormous star. It's very famous. It's fading. What were the theories as to what might be happening?
So there's a couple of different theories. One of them is that perhaps a part of the star is cooler than the rest, which is causing us to see it as a dark spot. The other one is that it could be dust. So dust could have been ejected from the star directly in our line of sight, and that could be blocking some of the brightness from the star.
What does the image tell us about which of those theories is right?
From the image, we can't tell exactly which of these two theories it is. So what we can do is explore both of them and see if we're able to match observations with simulations. So we can do some simulations with dust and see if any of them make sense and match the observations. And we can also do simulations where we change the temperature of the star in different places.
So you're basically building copies of the star in a computer and then observing them just as you do in the real universe.
Yeah, exactly that.
So what's happened to Betelgeuse since then?
Indeed, it has recovered. Of course, I was expecting the star to recover, but I was not expecting at all the star to recover so fast.
Interesting. So mysteries even in the recovery, which is fun. Now, I think if people know one thing about this star, it's that one day soon it will explode as a supernova. And when it started fading, there were people who thought that perhaps it would go supernova. Was that a possibility?
I don't think so. Basically, what is funny about stars and that we tend to forget is that anything that happens in the surface happened in the core like 1,000 years before. So anything that we see happening in the surface is not directly linked to what is happening to the core now. Ultimately, one day, it will explode sometime in the next 10,000, 100,000 years.
Okay, fair enough. Well, I guess that's reassuring for those of us who like having Betelgeuse in the sky. I was quite sad when it faded.
I think Miguel actually has the opposite opinion. So Miguel wishes on his New Year's Eve every year that Betelgeuse is going to explode as a supernova. And he made his last wish when we were at the VLT on New Year's Eve observing Betelgeuse. And he didn't quite get a supernova, but he did get some very interesting things happening to Betelgeuse.
Yeah, but actually, I'm not hoping for Betelgeuse to explode. I'm hoping for one red supergiant to explode because I'm too attached to this one. I cannot imagine Orion with a... It would be a tremendous show to see that, but I don't want this star to disappear. I like it too much.
I absolutely agree with you. Thank you very, very much. It's a fascinating story and a wonderful star. And as soon as you've worked out whether it's dust or a change in temperature, I hope you will get back to us.
It may be time to rewrite our accepted theories on the death of some stars. Observations of supernovae stretch back many hundreds of years, from ancient astronomers seeing bright objects in the sky by eye, But even until about the year 2000, we could only spot the more average ones.
It's only in the last few years, since we've had the technology to scan the whole sky every night, that we've started to detect really powerful and luminous supernovae. Astronomers recently announced the discovery of a supernova so bright, it was off the scale.
The supernova, called SN 2016 APS, was discovered in the constellation of Draco, in the far north of the sky.
Okay, that's recording. One more.
I spoke with the lead astronomer behind the discovery, Matt Nichol.
This supernova sounds amazing, but how do we usually detect supernovas, and how did you go about detecting this one?
So this supernova was found by a survey called Pan-STARRS, and this is a telescope in Hawaii. We were specifically looking for the brightest supernovae. It seemed to really come out of nowhere. There was no detected galaxy there beforehand. A bright thing appeared.
This image was taken before the supernova exploded. The green line shows where it would appear. Nothing had ever been detected there. And here, in the same patch, the sudden appearance of the supernova.
You've spotted this bright supernova. What did you do next?
Well, the first thing you do is to get a spectrum, and that tells you what it's made of, how fast it's moving, what kind of supernova it was, and how far away it was. So then we realized, when we had the distance, we realized that it was, not just appeared to be quite bright, but intrinsically was incredibly bright.
How long were you able to observe this supernova? Because standard supernovas sort of die out after a few weeks or a few months.
Almost 3 years, as we watched it very slowly fade away.
Wow.
It just kept going, so that was the real surprise. And it's when you add up all the light that got emitted over this long period of time, and you sort of count the energy, you realize that this was the most energy we've ever seen emitted by a supernova.
When it did finally die away, by looking with a more sensitive telescope, Matt was able to see where it came from.
It turned out to be very far away in a very faint galaxy. We had never seen this galaxy before, so this explosion kind of took us by surprise a little bit.
What does it tell us about stellar evolution and the stars themselves?
Yeah, so the total amount of energy that we saw just from the light show alone is more than standard theory of stars blowing up actually can accommodate. And there are old theories that kind of predict if a star was massive enough. There are more options available for how it might blow up. So we think we might have seen for the first time the explosion of a star many tens of times the mass of the sun, exploding in a whole new way beyond the standard theory of how stars die.
It's quite rare to make a discovery that literally rewrites the textbooks. Do you think you'll see more of these? Now that we've found one, are you hoping to find others?
Yeah, absolutely. So the first sort of stars born in the universe were probably more massive than the stars we see around us today. So these very, very bright explosions might be more common in the very distant universe. So if we could find one explosion from the first stars in the universe, that would be a huge result in itself.
New discoveries like this underline that we're learning all the time, and the universe still has many mysteries for us to unravel. Even our own star, the Sun, which we can study in exquisite detail, presents us with puzzles.
When we look at images of the sun, we sometimes see dark spots on the surface called sunspots, and they are beautiful to look at. They have dark, inky cores, and they're surrounded by these filamentary structures that make me think about petals around a flower.
But they're not always there. The number of sunspots varies in a systematic and cyclical way, from a maximum when the sun is heavily dotted to a minimum when it's completely blank. We call this the solar cycle. In fact, sunspots are the visible manifestation of the sun's magnetic field, which varies over this 11-year cycle. The sun is alive with dynamic magnetism generated and evolved by swirling currents of plasma in a process we know as the solar dynamo.
Each dark spot on the sun represents a patch of gas that has cooled down because powerful magnetic fields pierce through the surface. This evolution of the magnetic field through the solar cycle is like the sun's slow heartbeat.
And energy stored in the magnetic field powers the biggest explosions in the solar system. solar flares and coronal mass ejections. These events send out streams of high-energy radiation, magnetic fields, and charged particles that, when reaching the Earth, can ultimately disable satellites and disrupt our power.
So understanding and predicting patterns of solar activity is of vital importance to our modern world. Today we're at a solar minimum, and you can see that in this projected image the sun is completely blank. But in the coming months the activity will ramp up. It's just that exactly when and by how much is really hard to predict.
Our predictions at the start of the last cycle were widely off the mark. We clearly still have a lot to learn and need to improve our models of how the sun behaves. And it may be that we need some help from astronomers of the past.
Do you think it's the case that if we understand accurately what the sun's done over the last few hundred years, we can better forecast and predict what the sun will do in future solar cycles?
Yes, I think so. At least, in order to predict their future solar cycles, we need reference data. And in this historical analysis, we are improving the reference data themselves. And if their reference data is changed, then the prediction result will be changed as well.
Historian and solar physicist Hisashi Hayakawa from Nagoya University in Japan is trying to improve our 21st century models of solar activity by looking at historical records and drawings.
How challenging did you find it then to be having to look at all these different sources of information and interpret them?
We first have to decipher the handwritten text, and sometimes some people have not extremely nice handwriting. And in this case, it takes a lot of time to decipher what is written there.
Hisashi's research has taken him around the world in search of ancient records of sunspots. From the monasteries of Europe to India, China, Korea, and Japan. He has been delving through texts and drawings, often made by observers with little or no equipment.
I have recently consulted the naked eye sunspot drawings from local observer in Japan. And in this case, he explicitly stated that there was a mist and their solar disk was seen through the mist, and their mist played a role of the natural filter.
What do you think motivated these different societies to look at the sun?
The East Asian people thought that the supernatural phenomena, for them, including sunspots as well, are kind of a sign from the heaven. And if they see something spotty in the sun, that could be a kind of caveat against their contemporary emperors.
And where have you found the oldest records of sunspots?
The earliest naked eye sunspot drawing is created, I think, somewhere around 1140.
Wow! That's a beautiful drawing, isn't it?
Yes.
Have we improved our knowledge of the number of sunspots over time because we brought in historical data?
In the previous version, we had a kind of long-term uprising trend from 1700 to the modern time. But when we revise the sunspot number on the basis of the original records, such kind of uprising trend is almost missing.
So actually, you've dramatically changed the sunspot number. That's hugely significant.
Through this painstaking historical research, Hisashi and others have found a way to increase the precision and value of records that may on the face of it have seemed unreliable. And feeding this data into our modern models of solar activity is allowing us to refine our predictions of the solar cycle.
But will our improved and recalibrated data mean we have more accurate predictions? Well, only time will tell when we look back and see what actually happened in this new solar cycle.
If you want to take a picture of the sun, there's really only one person to turn to. Here's Pete.
I've decided that I'm probably not going to observe the sun at the moment. Now, I may not look as if I'm dressed for astronomy, but there is an alternate way of doing astronomy rather than staying up all night, and that's to go outside and observe the sun during the day. The sun, of course, is something we should never look at directly. We have to be a bit cunning. What I've got here is just a sheet of white paper, so I can put my hand up and it creates a shadow. Now I've got another sheet of white paper here, and if I create a tiny pinhole in it, let's see if I can do that. There we go. You can now see the circle of the sun, very tiny, but it is there. It's quite nice actually, it's not too bad at all, that. If there are any sunspots on there, a massive one, you would be able to see it. There are various ways you can set a telescope up to get a view of the sun, but you always have to bear in mind it's a dangerous thing to do. It can damage things, it can burn things. It could burn your camera, it could burn an eyepiece, and more importantly, it could burn your eyes. So you need to be really, really careful of that. Now, the first method I'm going to use is called solar projection. So basically, I'm going to use this telescope here, which is a 4-inch refractor, and I'm going to point it directly at the sun. The light is going to come out through the eyepiece at the bottom, and I'm going to project it onto a screen. And by a screen, I mean a piece of paper. And it's now in focus. There we go. So that is, believe it or not, an image of the sun. So another way of safely observing the sun is to buy a sheet of special certified solar filter material. It's about £20 for an A4 sheet, and the idea is that you make your own filter and then you fit it over the front of the telescope. Now, fitting that filter dims the sun's light by a huge amount, and that makes it safe to view through an eyepiece or using a camera. There it is, that's the sun. And about as boring as it could possibly be. There's absolutely nothing on it, but I will capture it for posterity. Okay, so that's observing the sun in white light. But there's another way of viewing the sun, using a specialty hydrogen alpha filter, which knocks out every wavelength of light apart from that given off and absorbed by excited hydrogen atoms. So it's a very precise filter, and it has to be made to incredible tolerances, and that's why they tend to be quite expensive. You can see as I'm moving down the image there that the sun appears mottled, and that's the chromosphere. That's hydrogen plasma, which is being manipulated by the sun's magnetic fields. If you can see that there are some huge structures here off the edge of the sun, and they are known as prominences there. Those are pretty tiny, has to be said. If you get a big prominence, it's really impressive and quite dynamic. You often see plasma, blobs of plasma, thousands of miles across. So there's lots of dynamic stuff to look for, and it's an amazing thing to do, which you can do all year round. You're not limited just to the summer, you can do it through the winter period as well, and you're never quite sure what it is you're going to get to see.
Tonight, we celebrate the life of a true star, Margaret Burbidge, who died in April this year at the age of 100. She was one of the key figures that help us determine we are all made of star stuff.
Burbidge's fascination with the stars began at the tender age of 4, when, on a family holiday to France, she took a night ferry, went outside and looked up. She was hooked from then on.
She later studied astronomy at UCL and started her career right here at the Mill Hill Observatory.
during the tumultuous days of World War II.
With most of the staff called away on wartime duties, it was Margaret Burbidge that was given the responsibility of keeping the observatory running, even though she was just a graduate student. Observing conditions were mixed. Perfect dark nights from the London blackouts, but also the constant threat of air raids. There's a famous log, which I know you've got out.
There is.
So this is one of my favourite documents in astronomy. Tell us about it.
This is a log that she took in 1944, August the 3rd. And in that period, London was going under some heavy bombings. And then it says, and I quote, at 21:44 GMT, flying bomb exploded very close and shifted star in declination out of field. At which point you'd expect most people to stop observing and
go home
for the night. Star recovered, exposure restarted, 21:47 GMT.
See, this gains her respect from observational astronomers. That's an amazing time.
After the war, she met fellow student Geoffrey Burbidge, who she later married. Together, they embarked on a journey of collaboration, which led to many new insights into stars and their chemical composition.
Most recently, we've been working at Lick Observatory, where there is a very fine new telescope, the 120-inch. It's a beautiful instrument. The observations I get with that, it makes me wish that I'd had access to this for very much longer. It's a wonderful telescope.
The pair went on to work with William Fowler and Fred Hoyle on one of the most important pieces of 20th century astrophysics. Margaret's observations were critical in establishing that elements as heavy as iron can be produced by nuclear fusion in stars. The result of all that work was a seminal paper with Margaret as first author, entitled The Synthesis of Elements in Stars. It's known universally today as B2FH, memorialising its four authors. It led Fowler to say that we were all truly and literally little bits of stardust.
Burbidge's successful career was not without its obstacles and challenges. She was refused access to the Mount Wilson Observatory in America, simply for being a woman. Her solution was to operate the telescope posing as Geoffrey's assistant, when in reality, he was assisting her. In 1971, she famously rejected the Annie Jump Cannon Award, an award just for women. She believed that there should be no discrimination for or against women.
Eventually, she became director of the Royal Greenwich Observatory, and then the first female president of the American Astronomical Society.
As a woman in science, she faced constant discrimination, but she remained undeterred and spent her life paving the way for future generations.
Her achievements here at Mill Hill, in nuclear astrophysics, and in championing gender equality in science continue to inspire countless others to pursue and achieve their own dreams.
Next month's episode is an hour-long special, where we'll be trawling through the archives, celebrating 40 years of missions to Mars.
Until then, good night.